Welcome to Lecture 2.1, Cyclic and Abelian Groups. In this series of lectures, we will introduce 5 families of groups: cyclic, abelian, dihedral, symmetric, and alternating groups. Along the way, a variety of new concepts will arise, as well as some new visualization techniques. We will study permutations and how to write them concisely in something called cycle notation. Cayley's theorem tells us that every finite group is secretly isomorphic to some collection of permutations, and that'll be at the end of this series of lectures. This particular lecture is focused on the first 2 of these families, cyclic groups and abelian groups. Informally, a group is cyclic if it can be generated by a single element, and it is abelian if multiplication commutes. And by this I mean if A star B equals B star A, and I want to say for all elements A and B in the group G. And even though I called this multiplication, it's this binary operation, which could be something like addition. So on to our first family of groups, cyclic groups. A group is cyclic if it can be generated by a single element. Finite cyclic groups describe the symmetry of objects that have only rotational symmetry. Here are some examples. Now we've seen this one before, and here are 2 more. So if we pick any one of these objects and we look at the group of symmetries, an obvious choice of generator for this group would be the following: a counterclockwise rotation by 2 pi over n. So let me just call that a click. So a click of this here is rotating this guy over to here and this to here. And similarly, a click of this object is a 90-degree rotation, taking this corner to that corner, and so forth. Here it's 2 pi over 8, so it's at a 45-degree rotation. Using that generator, we get the following presentation. We get the cyclic group, let's call it Cn, C for cyclic and n for the number of elements, is generated by a single rotation r, subject to r applied n times is just the identity rotation. One quick remark: this is not the only choice of generator, but it is a natural one. So let me ask you, can you think of another choice of generator? And if so, would this change the group presentation above? So the first thing you might say is, well, what about changing counterclockwise to clockwise? And of course, that works. Instead of rotating this pinwheel counterclockwise by 2 pi over n, we can rotate it clockwise, and that will generate every symmetry. However, we still need to apply that rotation n times, so we actually get the same group presentation. Now there is a more subtle choice of alternate generator in some cases, not in these 2 cases, but up here when n is bigger. So here n is equal to 10, I think, and let me pick r cubed for a generator. So let's call this the starting position. So, or let's put a 0 here and keep track of what happens when we apply r cubed. So if we apply it once, we get to 1, 2, we get it right there. I'll mark a 1. If we apply it twice, we get 1, 2, 3, we get it right there. If we apply it 3 times, 1, 2, 3, we get it right there. 4 times gets us 1, 2, 3, so there. And 5 times gets us 1, 2, 3. Now notice, doing this 5 times, and actually maybe to see what I'm doing, I'll do it something like this: 2, 3, 4. I think I'll stop here. I think that's messy enough. But notice that 5 times gets us halfway across, like a 180-degree rotation. So let's keep going. So 3 more times: 1, 2, 3. That's 6 times. Apply it again: 1, 2, 3. 7 times. again gets us 1, 2, 3, 8 times. 9 times gets us there, and then 10 times gets us back to where we started. So R3, so a rotation here of 2 pi over n times 3 actually generates all of these symmetries. But notice this also has the same presentation, because no matter what we call it, maybe we can call this thing big R, we get the presentation that C10 here is generated by big R, such that big R to the 10th is the identity. Here's a definition that we will use a lot. The order of a group is the number of distinct elements in it. So you can think of order as the size or the cardinality of the group, thinking of G as a set. So we use the same notation as we do for the size or cardinality of a set, just absolute value signs. So the cyclic group of order n, i.e. n rotations, is denoted Cn, as we've seen, or sometimes we will write it as Zn. For example, the group of symmetries for the objects on the previous slide are C3, that's the boric acid, C4 for the pinwheel, and C10 for the chilies. One quick comment, the alternative notation Zn for this group comes from the fact that the binary operation for the cyclic group can be thought of as modular addition. So to add two numbers in Zn, add them as integers, divide by n, and take the remainder. For example, in Z6, 3 plus 5 equals 2, and you can think of this as 3 clicks plus 5 clicks equals 2 clicks. If the context is clear, we may even write 3 plus 5 equals 2. So as we hinted on the previous slide, there are two ways to think of cyclic groups. One of them is additively, and the other is multiplicatively. So we'll do the additive version first. So a common way to write the elements in a cyclic group is with the integers modulo n. So 0 is the identity, and 1, you can think of it, if you prefer actions, as the single counterclockwise click. Observe that the set 0 up to n minus 1 is closed under addition modulo n. That means if you take any two elements or any two numbers from this set, add them together modulo n, the result is another member of the set. Here are some Cayley diagrams of cyclic groups using the canonical generator of 1. So to summarize, in this setting, the cyclic group consists of the set of numbers 0 up to n minus 1 under the binary operation of addition modulo n. The additive identity is 0. So this is going to be one useful way to think of cyclic groups throughout this class. The other natural way to think about cyclic groups is multiplicatively. So here, if we let R be a generator, and you can think of this as a rotation by 2 pi over n, now think of the symmetries in this sense, then we could denote the n elements multiplicatively as 1 for the identity, r squared all the way up to r n minus 1. Now you can think of r, if you've studied complex numbers, you can think of r as the complex number e to the 2 pi I over n, and the group operation being multiplication. Now this may ring a bell for some of you, and if it doesn't, that's fine, but if you have the unit circle, and then any number like this, e to the I theta, is going to be on the unit circle. Well, how do I want to draw this? Let me draw it up here. So if this is angle theta, then this number here, or this point in the complex plane, is e to the I theta. And if you multiply e to the I theta times another complex number, let's call that complex number z, which is some a plus bi. I don't really care to put actual numbers. And if I take z times a to the I theta, then that just rotates this complex number by theta. So it will rotate it up over here. So this here is z times e to the I theta. And this angle here is theta. In general, anytime you multiply complex numbers in the plane, their lengths multiply. So this thing, the length of this, the norm of this number is the norm of this times the norm of that. And by the way, this has length 1. And the angles add. So this angle from the positive x-axis, or real axis I should say, that angle is just the angle of this one plus, or rotated by theta, the angle of this. So going back to the unit circle over here, e to the 2 pi I over n, let's let n be equal to 6 for this example. So in that case, these are called the roots of unity. So this is e to the well, this is 1 obviously, so this is the e to the 0 times 2 pi I over n, and this thing here is r, which is e to the 2 pi I over n, and then this is r squared, oops, this is r squared, this is r cubed, this is r to the 4th, r to the 5th, and this is r to the 0, or r to the 6th. And I'll let you fill out what the rest of these are. So this is e to the 4 pi I over, and I said n, I should say 6. Let's see if I can fix these into a 6. There's a 6, and there is a 6. And one more, there's a 6. Okay, so we'll see more complex numbers later, especially when we study Galois theory. But for now, let's get back to cyclic groups multiplicatively. So note that r to the n equals 1, of course. R to the n plus 1 equals r, and so forth. So do you see modular addition rearing its head again, even though we're multiplying things? It's in the exponents. So here are some Cayley diagrams using the canonical generator of R. So these should look just like the last ones on the previous slide, but the previous slide we had, remember, 0, 1, and 2, 0, 1, 2, and 3, and those numbers now appear in the exponents. So to summarize, in this setting, the cyclic group can be thought of as the set of these numbers, these are complex numbers, under the binary operation of multiplication. Or if you want to just call this R, that's fine. The multiplicative identity is 1. So one of our notations for cyclic groups is additive and the other is multiplicative, but this doesn't change the actual group. It's only our choice of notation. One more remark. There is a unique infinite cyclic group, which, if you think of things additively, is just the integers under addition. If you want to use multiplicative notation, then you can think of the infinite cyclic group as the following. G is generated by one element R subject to no relations. In other words, it is the set of all powers of R where k is some integer. So this group contains r squared, r cubed, r to the 200, r to the million, contains r to the negative million, which is the inverse of r to the million, and so forth. For the infinite cyclic group, let's use additive notation now. Only 1 or negative 1 can be generators. Because if you use anything else, if you start with 3, you can never get back to 1. So if you start with 3, you generate 3, 6, 9, 12, and so forth, and their inverses. Of course, you can use multiple generators. You can use 2 and 3 as generators, and you can take 3 minus 2 to get 1, but that's usually pointless. If it's a cyclic group, we usually only want 1 generator. So here's a proposition that you may have already figured out by looking at my previous example with the 10 chilies. So any number 0 up to n minus 1 that is relatively prime to n will generate Zn. For example, 1 and 5 generate Z6, while 1, 2, 3, and 4 all generate Z5. Now, if we want to use our notation, we can say Z6 is generated by 1 and generated by 5, and Z5 is generated by 1, 2, 3, or 4. Now, one important note here, this notation is not a group presentation at all. This is when I first introduced these brackets, what I meant them to say was generated by. So Z6 is generated by 1. Z5 is generated by 3. That's all that means. It's shorthand. And finally, one more thing. Since we looked at the group Z10 when we looked at those chilies a couple slides ago, let's go back to this proposition and see what generates Z10. So Z10 is generated by anything relatively prime to 10. So 1, 3, not 5, but 7, and 9. And remember, I convinced you that 3 generates it, but I did not convince you that 7 does. Let's say a word about the multiplication tables of cyclic groups. So modular addition has a nice visual appearance in a multiplication table of cyclic groups. This is probably something you saw in your addition tables when you were in elementary school, or at least patterns like this. You surely noticed this. There are many things worth commenting on. Well, maybe not many, maybe just a few. But one of the most important properties of the multiplication tables for cyclic groups is the following, the one you've probably already noticed. If the headings on the multiplication table are arranged in the natural order like it is above, I don't care if you want to use additive notation or multiplicative notation, then each row is a cyclic shift to the left of the row above it. And this is probably something that you've already noticed when you were back in elementary school and you had addition tables up on your wall. Do you see why this happens? Of course you do. We started our discussion in this series of lectures with cyclic groups because of their simplicity. This is the simplest family of the 5 that we will see, but also because these play a fundamental role in more complicated groups. Before continuing our exploration into the 5 families, let's observe how cyclic groups fit into other groups. And we'll do this with an example for D3. Here's the Cayley diagram on the right. And let me ask, do you see any copies of the Cayley diagram for any cyclic groups in this picture? So here's one. If we start at the identity, here is a copy of a cyclic group right here sitting inside this group, E, R, and R squared. And we refer to this cycle as the orbit of the element R. So when you take R and you keep applying R to itself, we don't get the whole group, but we get these 3 elements. We get a copy of a cyclic group inside. Now look at the blue arrows. We start at the identity and we apply F, we get a length 2 cycle. These 2 elements, that is the orbit of F. Orbits are usually written with braces because I want to emphasize the fact that they are sets rather than ordered sets or anything like that. So in this case, the orbit of R is this set of 3 elements, and the orbit of F is this set of 3 elements. So the orbit is the orbit of an element is all elements generated by that element. So every element in a group traces out an orbit. Some of these may not be obvious from the Cayley diagram, but they are still there. So let's work out the orbits for the remaining elements of D3. So we've done E and R. Let's start with R. So if I can only apply R squared, I get R squared, and then R, and then back to the identity. So the orbit for R squared is actually the same as the orbit for R. Even though I've written them in different orders, these are the same set. Now the orbit of RF, so let's apply RF, RF, and then RF, and we get back to the identity. So it's just this 2 element set. And the orbit of RF squared, let's try that, R squared F. R squared F, R squared F, again, just traces out these 2 elements. Note that there are 5 distinct orbits. Even though I've written 6 here as sets, these 2 things are identical. A few slides ago, we defined the order of a group to be the size of the group. So now we're going to define the order of an element with the same notation, this absolute value sign, to be the size of its orbit. Mathematically, that is this. The order of G is the order of the cyclic group generated by G. And again, this absolute value means order of this group. So the order of the group is defined to be that. Note that in any group, the orbit of the identity will simply be just the identity. In general, the orbit of an element G is the following set. So it's the cyclic group generated by G, so it's the set of all powers of G, where K is any integer. So this looks like I'm writing an infinitely long list of elements, but as we've seen with the finite cyclic groups, this set is not necessarily infinite. Like, for example, we can frequently have something like if r to the fourth is the identity, then r to the first equals r to the fifth equals r to the ninth equals so forth, and this set right here only has size 4. Now we allow negative exponents in the orbit of G, or in other words, in the subgroup, cyclic subgroup generated by G. Though this only matters in infinite groups, because remember, for finite groups, like in the C10 example, r to the ninth equaled r to the negative 1. And in general, r to the n minus 1 equals r inverse. In other words, rotating one direction n minus 1 times is the inverse of rotating the other direction. Because notice, if I multiply either of these things by r, I just get r to the n, which is the identity. In other words, this times r is this times r, that is r to the 0, and that is r to the n. Both of those, make the 0 a little bit better, both of those are the identity. One way of thinking about this is that the orbit of an element G is the collection of elements that you can get to by doing G or its inverse any number of times. So if you think of this in terms of Cayley diagrams, if G corresponds to maybe the red arrow, or maybe it's not an arrow, maybe it's a path of maybe the red and then the blue arrow, then the orbit of G is everything you can get to by following all of the G paths, forward and or backwards, as much as you want. So one more remark, in any group G, the orbit of an element is a cyclic group that sits inside the big group G. I think I've already said this a few times. This is an example of a concept called a subgroup, which is something that we will study in more detail later. It's a smaller group sitting inside a bigger group, like a subset. So since this is visual group theory, we're going to see a way to visualize orbits in a different way. And I think this is best done with an example. And let's start with D3, which is what we saw before. So here there are 5 orbits. Remember that these two are the same. So we can arrange them with cycles like this. And notice that I do not put arrows on the cycles because I want to emphasize these are sets. These are not necessarily directed sets or ordered or anything like that. So a few comments. In a cycle graph like this, or also called an orbit graph, every cycle represents an orbit. That's an orbit, that's an orbit, that's an orbit, and that's an orbit. But wait a second, we have 5 orbits, not 4, right? Well, hold off on that. The convention is that orbits that are subsets of larger orbits are only shown within the larger orbit. So for example, if we had the cyclic group C4, then the orbit graph would be E, R, R squared, let me fix that R, and R cubed, and these things would be, let me use blue here. So this is the orbit of R, and also the orbit of R cubed. Both of these things generate this orbit. Now R squared generates an orbit, so the orbit of R squared would be E and R. So you'd think that we might need to draw a cycle like this to denote that, well, we have a 2 cycle here, and we have a 4 cycle here, and maybe we also need a 1 cycle because E is in its own orbit. But we usually don't draw those, and that's what we're doing up here. So we don't actually draw, we don't need to draw that this little 1 cycle to denote that E is in its own orbit. And typically here, we don't need to draw these subset orbits at all, because we know that they are always included. Now we don't put color or put arrows on the edges of the cycles because one orbit could have multiple generators. Like here, R or R squared will generate this orbit. And sometimes we might have the case where our Cayley diagram has 2 different generators. One has a red arrow, one has a blue arrow, and both of those appear in the same orbit. So we certainly don't want to put colors on the edges. Now intersections of cycles show what elements they have in common. Like this 3 cycle and this 2 cycle, they intersect in one element because that's the element that is shared by both of them. So question, what do the cycle graphs of cyclic groups look like? Well, I guess I've given away that a little bit. It's going to be just one big orbit, one big circle. And as I said before, we don't need those suborbits because, well, by this second comment right here. Now, our second family of groups are the abelian groups. Recall that a group is abelian, something that is named after Niels Abel, if the order of actions is irrelevant. So we say the actions commute. Here's how to formalize this mathematically. A group is abelian if AB equals BA for all A and B in G. And here we are assuming that the operation is multiplicative, though that does not need to be the case. Abelian groups are sometimes referred to as commutative because the actions commute. Personally, I find that word hard to say, and for whatever reason, most people call these groups abelian rather than commutative. Now, to check that a group is abelian, down here, it suffices only to check that this property holds for all generators. Think about why that is. Well, if you know that this property, this abelian property holds for all generators, then it's clearly going to hold for all words or all elements in the generators. The pattern on the left never appears in the Cayley diagram for an abelian group, no matter what your choice of generators is. Whereas the pattern on the right illustrates the relation that AB equals BA. So Cayley graphs of abelian groups are going to have all sorts of patterns like this in them. So a few examples. Cyclic groups are abelian. One way to explain this is that the left configuration on the previous slide, that was this one, in other words, where A, B, and B, A were different, can never occur because there's only one generator. You need 2 different colors or 2 different generators for something like this to occur. Another reason is in the cyclic group generated by R, every element can be written as R to the K. And clearly, R to the K times R to the M equals R to the M times R to the K. Both of these things are equal to R to the M plus K. Now, it is important to note that the converse of this statement up here fails. Though cyclic groups are abelian, abelian groups do not have to be cyclic. Remember V4, the Klein 4 group? That's a good example of this. So there we had a group of order 4 where you needed 2 elements to generate it. Let's explore this a little further. The following are Cayley diagrams for 3 groups of order 8. So this is a group called C4 cross C2. We'll talk about what that means later. It's actually called a direct product. So this is a group we have not seen. And these are 2 groups that we have seen. This is the dihedral group, and this is the quaternion groups. Are any of these groups abelian? Let's start here. So red, blue equals blue, red. And we only need to check that once. That pattern will permeate throughout the diagram. So this one is abelian. Now we know D4 is not abelian, right? Red, blue is different than blue, red. Okay, done. And what about Q4? So let's start up here. Red, blue, and blue, red. those are different, this group is not abelian. Recall that cyclic groups are easy to spot from their multiplication tables, and so are abelian groups. The property that AB equals BA for all A and B, in other words, the characteristic of being abelian, means that the table must be symmetric across the main diagonal. I think this picture is truly worth 1,000 words. I don't need to say much to explain that. And so here's an example of a group that's abelian. It's also cyclic. So we noticed previously that each row here is a cyclic shift of the previous one, but we also noticed that this obviously has this symmetry property, namely that it's symmetric across the main diagonal because it is an abelian group.